We are here to listen to Professor Michael Kirley's talk on the grounds of the injury of coordination, who has never seen there before or before. And we pay respect to the elders, past, present, and emerging. Welcome to Michael Kirley's talk. He is a very long-term friend of mine, and which work together. But I know him for probably about 20 years. And he's the director of Melbourne Centre Data Science, as you know, on the same floor as ours. And he's a professor at School of Computing and Systems. He's a very well-known and renowned agent-based modeler. And so when he said he was going to talk about the various data science projects that our center is involved in, I said, well, why don't you talk about agent-based modeling? We'd love to hear that. So managed to twist this out, and here we are. So his talk is going to be about agent-based modeling, an important data science.
So thank you. I guess I should start by just emphasising with this referendum coming up, you guys are in a position to actually inform people, so I'd encourage you to do that. I know lots of people out there who have absolutely no idea that there's a referendum on. That might sound strange, but in the university, we live in this sheltered world. I'm going up to country Victoria on the weekend, and I'm sure most of the people there will be really amazed there's even a referendum on. That might sound strange, but okay. Agent-based modelling. And I was not going to talk about agent-based modelling. You're right, Yoshi. Because my PhD was in optimisation. A lot of the work I do is all about decision-making. And I spend a lot of my time doing mathematical models to work out, is this the right path to take or whatever. And agent-based modelling was always just sort of in the background with my work. And then I met Yoshi, as he said, about 20 years ago, and I sort of spent a bit more time working in the general area of evolutionary game theory, playing games on graphs, looking at emergent dynamics. So what I'll do today is talk a little bit about some of that work. And what I've elected to do is just take a snapshot of 3 or 4 small agent-based models that either I've been working on or some of my colleagues in the Melbourne Centre for Data Science have been working on. So I'm not going to go into lots of details about any particular model. I just want to talk about some of these models we're working on and talk about how we use agent-based models and the limitations of agent-based models and possibly the advantages of agent-based models. I'm glad Van's here. I'm going to use her as an example of something a little bit different. Last year, we ran a panel session in the Melbourne Centre for Data Science and MDAP, and it was about complex data. So don't call out an answer yet, but just think about it. To you, what does the term complex data mean? And Van was one of our panelists, and we had some other guys from astrophysics and neuroscience, and everybody came along and talked about what makes data complex. Is it because it's large? Is it because it's small? Is it because it's heterogeneous? Whatever. There's a whole range of different factors there. But sometimes we don't actually have data. We have to generate our own data to solve problems. And agent-based models are one tool that we can use to generate data to explore particular hypotheses. So that's something I'd like to talk about. A couple of weeks ago, during the Innovation Week, the Melbourne Centre for Data Science and MDAP worked as a team, and I was running a session about data integration and bias. So this theme in agent-based modelling is really important. How do I integrate different data sets together? And when I build my agent-based model, is there some sort of bias in those models as well? How do I deal with it? So this talk is really going to be fairly generic about agent-based modelling. But before I do that, if I can click, I want to talk for 3 or 4 slides, maybe 5 slides about Melbourne Centre for Data Science. And the Centre is a joint initiative between 2 schools and 2 faculties. And this is a really descriptive term. It's a pain in the bum when you're working across the university in 2 schools and 2 faculties to get things to work. So my research, as I said, optimization, done a lot of research in evolutionary game theory, and I spend a lot of time looking at uncertainty in these models. Howard Bondell, who's head of maths and stats, is the other co-director of the centre, and his work predominantly is in Bayesian statistics and uncertainty. So combined, we provide this overview of the centre, different threads about how we tackle data science questions. Howard's he's very strong in the statistical techniques. I have statistical background as well, but my emphasis is really in the machine learning side and optimization. Our team is made up of a variety of people: research fellows, academic conveners, investigators, and PhD students. And that's really important for this presentation. So Chris Baker in the top corner there is a senior research fellow in the centre, does a lot of work in the COVID modelling space for over many, many years, and has developed a large number of agent-based models as well. And TK is a research fellow who works with them. So I want to talk a little bit about one of the models that they did to inform policy. Fiala is a research fellow working with me. And if I just add a few more people there's a few of these people online today. So Jason Thompson has done a lot of work in agent-based modelling and computational social science, certainly in that COVID space as well. Irma, down the bottom here, is a professor in arts. I think it's social and political sciences. And why I've listed her there is at the minute, Fiala and Irma and Jason, to some extent, we're building a whole range of agent-based models focusing on underemployment and unemployment. I cannot go into the details of those models at the minute because we're about to apply for funding on the particular things there, but I'm happy to talk about that offline. Some of these other faces you will notice around level 8 all of the time. The important thing about this particular slide is the centre is relatively small in terms of full-time research fellows. But the important thing here is we run a whole range of activities and we link into the 2 schools. That text at the bottom is really, really small to annoy you, but go onto the webpage and look up a reading group associated with agent-based modelling and computational social science. Jason is running that. I'd encourage you all to come along and have a conversation there. I notice a few faces here who have been in that particular group before. What do we do? Because I'm a machine learning person, optimization person, I like to look at uncertainty and trust in algorithms and bias in algorithms and so on. So a lot of the research I do is actually driven by that. How can we extend the methodological frameworks in data science? That's my particular aspect. If I take Howard's aspect, it's more about those statistical models. Through the centre, though, we spent a lot of time working with partners where we use standard, in quote marks, data science techniques to tackle particular problems. And that's where that data integration part comes in and where the agent-based modelling part is going to come in. Perhaps I have expertise in some of these things. I don't have expertise in all of them. As we go across, expertise in some of them, not in all of them. We go across, expertise in some of them, not in all of them. But through the centre, we work with School of Mathematics and Statistics, the School of Computing and Information Systems to frequently set up teams of researchers to tackle these problems. On this particular slide, when I'm zooming in on the agent-based modelling part, the uncertainty, machine learning, that's really what I'm going to be talking about now. One other part that's missing is that causal inference. And over the last year or so, working with Frank Fatiri, who's a professor in my school, and Fiala, we've been looking at a whole range of causal discovery problems. And the domain has actually been related to the work with Irma on underemployment and unemployment. We've been concentrating on the causal discovery part and building counterfactuals, but the reason we're doing that, it's going to be input into agent-based models. So why am I sort of saying that right now? When I'm going to build an agent-based model, we make a whole lot of assumptions about what we're going to do. What are the rules? What are the interactions and so on? How do we inform what's going into those rules? How do we inform what's going to go into the behavior? So just off this slide, we've spent a lot of time concentrating on issues associated with causal discovery in really large data sets so that that information can inform what we're going to do when we hit the agent-based model. So that's a really high level overview of the centre. And I'm happy to talk in detail about any of these things at another stage if you want. 3 slides just talking about our partners. So I'm not claiming Melbourne Centre for Data Science solves all the problems associated with Doherty and whatever. But the reason it's here is, it's this, if we're going to make inroads or make serious contributions, we have to be working in teams. So Chris and TK are based in our centre, working very closely with the team at Doherty. And this is not the whole team there, of course, building some of these models. Can you put your hand up if you're sick of the TV screens on level 8 with Optima? And I'm not in any of the videos. That's what's really annoying. So I'm also a Chief Investigator in Optima. And the project I'm working on is with Department of Defence. That's why it's not on the video. The other research institute that I work with really closely is another ARC centre, which is the Digital Bioprocess Development Hub. This is run out of chemical engineering with our industry partners. If you look outside our building, you'll see CSL. So we go and work with those guys as well. Optimisation, digital bioprocessing. Okay. We build models to help them solve problems. We're not necessarily building an agent-based model to tackle a lot of the problems in this biopharmaceutical industry. But often we're using mechanistic models, coupled ordinary differential equations to do a whole lot of stuff and vary the parameters to see what happens, make some decisions. There's lots of similarities with what we do with agent-based models. If I was to go right back to the first slide, I put up something about agent-based models as a toolkit for computer scientists or data scientists or whatever the title was. I would like to change it now from rather than just saying agent-based models, but I want to talk about autonomous agents and multi-agent systems. So the work with Optima and this group falls under that umbrella a little bit more than just thinking about standard computational models that perhaps you guys are really familiar with. My last slide about the centre and where we all fit together. I noticed some of you have been in presentations where Ed and James have been talking about the direction of AI at Melbourne and trying to set up the equivalent of an institute or where we're positioned. So a lot of the work from Melbourne Centre for Data Science, working with CADE up on level 8 as well, links in under these themes. And obviously you guys do a lot of the work in this space as well. So certainly not silos, but how do we all work together to solve the problems is what we're talking about. What I'm going to do is just flash up 4 sample projects, then it's 4 more sample projects. If I just pick one project as an example, optimal sampling for invasive species management. Without going into the details of the model, you can all just imagine what might be going on in something like this. Let's just think about, I'm making up a scenario now. This may not be true. Let's consider species invading the top of Australia, plant species or whatever. So if we're going to try and model something like that, what would we possibly do? If we change it from plants, let's talk about cane toads or whatever. What are we going to do? So we've got some spatial model. You've got some invasive species that's going to behave in a particular way. We need to come up with abstract rules. We're going to map them all together. We're going to run our simulations to see what happens. I'm assuming that most people in this room have some experience with agent-based models. So it's not meant to be a tutorial on agent-based models 101. So armed with that, that's the sort of thing. These other projects, I sort of mentioned that underemployment, unemployment sort of situation, the causal modelling comes in there. So there's lots of examples. If I have time today, I'll come back and talk about one of the projects with a PhD student I'm working with, Craig. His co-supervisors are in Melbourne Business School. I'll talk about what's going on there, assuming we have time. Last one, and Yoshi said, talk about agent-based modelling. But this isn't agent-based modelling, but it's something that's taken up my time over the last 2 years. And if you've been paying attention over the last week or two with the NDIS Royal Commission stuff, it's been a big project through the Melbourne Centre for Data Science where we've been collaborating with experts in the university and other universities around Australia, trying to build a new training program to help practitioners in this space. Not an agent-based model, but hey, something to take all my time. So let's focus on what you guys really want to hear. I love this picture. I coordinate the Masters of Data Science industry projects. We have about 40 projects each year where the students' capstone teams go out to their industry partners. Basically, on the right-hand side, this is what the industry partners want. Go and process the data, guys. Come back and tell me, which are the most important features in my data set? Can you do some correlation analysis? Can you go and use your fancy whiz-bang AI tools to do a regression model or a classification, whatever? And they're all really standard sorts of projects and they're fun. Lots of insights. We run these AI tools, whatever we're going to do, they're data science models, statistical models, whatever they're going to do to make some sort of a recommendation. If we know what the parameters and variables are, it's all fine. But the challenge is, how do I integrate that data? If the data is noisy, missing values, if it's heterogeneous, we have large data sets, how do we put them all together? And that's what one of these challenges are. In the problem domain, well, what is the problem domain? Excuse me. Quite often, data scientists really do not understand the problem domain. They're really great at pushing a button on their notebooks or whatever it's going to be and spit out some data, but do they really understand the problem domain? So that's what takes a lot of time from my perspective when I'm working with industry clients and other clients around the university, is trying to understand what's going on. The surrogate model part is really the most interesting part of this for me. Sometimes we have to build some approximation of the system, some approximation of that problem domain. That surrogate model, quite often for me, is some complex system of ordinary differential equations mimicking that system. But sometimes that's not necessary. Sometimes we can use a simpler version of just coding a whole series of rules and coding a whole series of interaction patterns, our standard sort of agent-based model approach. I borrowed this slide from Jason the other day, so I should have acknowledged that there. What is an agent-based model? So we've got this interaction between our numerical methods and a particular discipline. And here it's written as a science discipline, but perhaps it could be anything. And this Venn diagram, in effect, to me, just encapsulates data science generally, where we're applying computer science methods, statistical or other numerical methods, working with a domain expert to build some sort of a model. That's what we're doing with our agent-based models. That's why I've indicated I believe it's an important toolkit for all data scientists. So what we're going to do is build a computational model of some system. The fidelity is really important. We are not trying to reproduce the system exactly. If we're trying to reproduce the system exactly, perhaps an agent-based model isn't the right tool to use. I totally hate line 2, as if it's an intelligent entity. But when we look up definitions of agent-based models, typically we talk about these intelligent entities interacting in some way. But what we're going to do is encapsulate a whole series of fairly simple rules. What I want to emphasize today is I'm going to go from really simple rules to lots of processing in the background in those rules. The autonomous agent part, the part that I think is a little bit more exciting. The rules can be derived from existing research evidence or expert opinion. Linking back to the work I mentioned with causal discovery, we were trying to use some evidence-based approach to inform what the rules were going to be. So agent-based models. So we're going to have this group of individuals interacting in some way. I've deliberately left off the word emergent behavior there because I find emergent behavior really frustrating as well. Do we write emergent because we don't know what's going to happen? I don't know. We want to use the rules to generate patterns, and then we want to interrogate what's happening. Is emergent because you just didn't understand what you were doing, or is it a surprise? But then go to coupled ODEs, you get really interesting chaotic behavior. So I'm not really criticizing emergent. I'm just a little bit hesitant to put it on my slide there. So 3 or 4 case studies. So before coming along, after Yoshi really put pressure on me to talk about agent-based modeling, I went to the team and said, what's a really nice case study to talk about? So Isabel's a PhD student who's been working with TK and Chris on this particular project. So perhaps I may not do justice to their whole model, but I guess I'm going to use it to illustrate what's going on when we build these agent-based models. Hybrid immunity, what's going on? We know about vaccinations, we know about infections, you know about, hopefully all of us went to have multiple doses of vaccines and so on. And then that question comes along, should I have more? Do I need another one? There's going to be a new variant. What's going to happen? So we know we've got this complex landscape. What's going to happen? So given all the past immunity, do we still need to vaccinate? And if so, who, when, what should happen? So these are questions that you guys have been thinking about for a long time. And why I chose this particular piece of work is it's a fairly serious piece of work used to advise governments about what's going on. But that detail is not what I really want to concentrate on. I want to concentrate on the methodology that's being used a little bit and how assumptions are made in the models. There's limitations and those sorts of things as well. So in order to do this, we need to consider some sort of a pipeline about what's going on. So we've got some model of, the infection model out there. We have to have some sort of model about transition through the population. We need to have some sort of model about the clinical pathways. And unfortunately, in the real world, everything gets down to money. This is an expensive sort of business. How do we save lives? But how much is it going to cost us as well? So there's input into these things. Of course, there's a whole range of clinical studies. And this is where I'm emphasizing my role as a data scientist again. We're not meant to be the experts in all of the clinical studies, although we have to interface with them to work out what's going on. Then when we come to the population transmission level, there's a whole range of factors in there. Age distribution of the population, etc. Then as we go through that clinical pathway, what are the possible outcomes? And then finally, when we combine all of these things together, what's the decision we're going to make? How do we inform the decision? So the team here has built the agent-based model to do this. So we're not doing the whole pathway. If you like, input into the agent-based model relies on expert opinions. We're feeding them in. I'm not going to go through the detail of the model, showing you the pseudocode and all of that sort of stuff. It's just high-level picture. So typically in our agent-based model, we have the equivalent of attributes for the agents, unique ID, and factors which we're really, really interested in. So the age attribute, what level of antibody neutralization has occurred there, history of infection, and so on. So we've got an individual agent, attributes. Then eventually we're going to map them onto some social network or some grid world, and we're going to push a button and let the model run. Before we do that, it's important that we identify what are the interaction parameters between the individuals. So in this particular slide, the text is a little bit small to see, but we've got age, different levels for older participants versus younger participants. What's the likelihood of them interacting? So the point of the slide is it's a little bit different. Now, as we know, if you're going to map agents onto social networks or different graph structure, of course the graph structure is going to have some impact on what happens. And there's lots of theoretical papers that talk about diffusion on the networks and whatever, and most of you would be familiar with that. But when we're building our models, it's really important that we consider those sorts of things. We go through. So perhaps one of the most important attributes in this model is about the susceptibility to new infections, what's going to happen with the transmission, and also the severity of the disease. So we go on. This is actually quite timely for me, and I said this to Yoshi the other day. 2 weeks ago, my son actually went to ICU with COVID. And at the time, I thought COVID was over. So it's really timely that this question about vaccination, whatever, is still there. So there's the outcomes. But what happens building this simulation model is, well, there's two populations here. These are not real populations. They are synthetic populations derived from real-world parameters, so that we have a population which is skewed towards a younger population versus older population, or drawn from valid statistical models to see what happens. So now, backtracking a little bit, we've got our individuals in the population, we've got our interaction matrix, we know what the outcomes are going to be, we can change that interaction matrix, skewing it to particular age values, and away we go. The details of what's actually going on here are not that important for today's presentation. When the guys did this presentation, this was the most important part. As I go through, you can see here the colour of grey is just talking about the variant of the COVID spreading through the population. And the trends, it's a little bit hard to see on this particular slide, but I've got 4 different values of whether there was further boosting, paediatric boosting, high-risk boosting, or random boosting. And as we go across, you can see fundamentally, there's not a lot of difference between them. And of course, if I change parameters, different transmissible rates, I get slightly different values corresponding to each of the rows. And then we delve in a little bit deeper and do its further statistical analysis. And in fact, there is a significant difference for the high-risk boosting in a particular case. So from that, a decision can be made about the cost effectiveness of what's going on. So the take-home message from my part of the presentation using this case study was that when we're building the model, if I backtrack, because I think this one's really important, when we build our agent-based model, we don't want to have really high levels of fidelity in here, although I omitted all of the fine-grained details of how the model works, but it's clearly informed with what's going on out here. And working out the most appropriate population structure is crucial. Case study 1. Case study 2. Only a toy model. So this is a project being done by a grad student, Amy, and Alex, who some of you may know, who's an MDAPper up on level 8, who has expertise in archaeology work. What's going on in this project? ABMs on the roads of Roman Britain. The inspiration for this work was a paper in PNAS a while back about how can we use agent-based models in archaeology to inform what's going on. This is a very, very different domain. The text is a little bit small, but there was 2 papers. The first paper was talking about the role of interaction networks, the road network in ancient Rome. Oh, sorry, Roman Britain, I'll get that correct in a minute. And there's a particular itineraries, which we'll talk about a little bit in a bit more detail in just a minute. And then there was another paper which was talking about the interaction strategies of people back in whatever year it was. Again, see how I'm not an expert in the domain. What are we doing in the project? Here we have some geographical network, which is documented in the literature. We don't really know whether it's true or not, about particular road networks. Then we have other distributions documented in the literature about pottery distributions. So what Amy is doing in her project using agent-based models is how can we explore whether there's some sort of correlation or approximation about this distribution of pottery on these roads. So she's not trying to solve all of the problems about Roman Britain. It's impossible. But what she's trying to do is use an agent-based model as a bit of a thought experiment to simply say, is it possible that we can use some sort of a simulation model to approximate that distribution of pottery across Roman Britain? Why did I use this example? It's because of this methodology that we're going to use, and it's a fairly standard approach. So we have 2 different geographical networks. One of them at the top, that itineraries, is documented Roman Britain. There's an alternative one there. I don't know which one's correct. They're both accepted in the literature. Going back to some of the research papers, they start talking about, I've put it here as communication networks, but the interaction networks in marketplaces back in year whatever it was. So what we're going to do in this project is, can we combine these in some sort of appropriate way? So it's the multi-level coupled network approach to solve the problem. So the methodology is fairly standard in agent-based models. So I've got my spatial network, wherever they come from. And in effect, there's some parameter here associated with distance. Then I've got my particular social networks. And in our model we're playing with here, we don't know what the real social networks were, but we can combine them together. When it comes time to look at decision-making, we combine these together. If I went back to my very first slide when I introduced our research conveners, somebody I didn't mention was Martin Tomko, who does a lot of work in spatial data analysis. So if we extend this toy model that Amy's been working on to the real world, these spatial models can in fact be real models associated with current days. These social networks, you guys provide input into that sort of space. How do we combine them all together to solve particular problems? Usual standard, or the usual sort of approach to agent-based modeling, we have a whole sweet load of parameters there. We're going to go and play and vary the parameters and see what happens. And we do systematic sweeps across them and so on. So here is another map showing the distribution of pottery in Roman Britain. We do our simulation models. Let's zoom in on one of those simulation models. Here we have a situation where we made an assumption that 3 different types of products were in this system. One was manufactured in London, one was in Winchester, one was in York. They interact, they trade, and we get the distribution of pottery. And then finally, because it's an agent-based model, we're able to go and change a whole lot of parameters to see what's the effect of the decision-making strategy, change the social network, see what happens. This is very, very different to that COVID model. It's completely made up magic. But that's the point of it. It's a thought experiment to try and inform what's going on. There's no way we can validate a model like this. And that's the key point that I was trying to make here is we build our agent-based model as a thought experiment. Almost always we want to validate them, but we can't validate this. Does it mean it's useless? No. It just has a completely different purpose. This is a real engineering project. I'm not going to go into the details of the engineering project, but imagine you all have some idea of what I mean by sustainable urban freight systems. The pictures, Joyce is a lecturer in maths and an OPTIMA person. The research area is optimization, routing traffic and so on. Russell Thompson is a professor in infrastructure engineering who's built his whole career in this space about modeling transport networks. So what I want to talk about now is an agent-based model on steroids. It's no longer going to be a simple computational agent-based model, but the computation is actually going to be quite complex. And I'm going to do it without any formulas. You must be sick of that if you travel on the freeways. It just does my head in. Then at my house, I don't know what happens, but we get parcels delivered all of the time. I imagine most of you have got parcels delivered, and it's just out of control. Right? So what we're talking about here is we've got this congestion, lots of parcels being delivered. What can we do about it? It's that bigger question. Now, obviously, as me in Melbourne Centre for Data Science, I cannot solve that problem. But working with a larger team, our goal is about how can we improve our understanding of how this whole freight system works. Not just understanding what's being done now, but if there was some sort of approach to introduce some new collaborative approach to route all of these parcels through the traffic and whatever, what could we do? Now, obviously, when we're talking about such large infrastructure, we cannot just go and make a change. So a simulation approach seems like a very sensible thing to do. So the goal of this project is really about building an integrated modeling framework to explore this stuff. The 3 steps here are crucial. We're going to build an agent-based model to do this. But in order to build this agent-based model, we have to work out what those behaviors are going to be. So in this particular case, we're going to use gamification. So our stakeholders are going to be engaging in particular games so we can observe their behavior, build some sort of discrete choice models and so on. And that helps us determine what the rules are going to be for our agent-based simulation model. The digital information modules is we're really talking about real-time traffic monitoring systems here. So this is why it's a joint project with infrastructure engineering. It's not something we can do just like that. So if I talk about a pretty basic sort of model, I've got a blue carrier and an orange carrier, vehicle routing problem, traveling salesman type problem. I've had 2 or 3 PhD students work on this sort of problem. Turn it into a dynamic optimization problem, and they've got their whole thesis out of it. It's all, I enjoy it. Now, our scenario for this novel logistics is going to be, hey, let's start considering gig economy or, other people being involved in this process. Rather than having one truck running around Melbourne that's half empty, how can we fill it up, or how can we share what's going on? It's that sort of picture that we're talking about. Caveat again, you cannot get these independent contractors to start sharing all of their information together. It's just not going to happen. So there's a whole range of questions in here about what's the best route you're going to take? Where do you start from? What price are you going to charge? What's your fleet size and so on? How do you use crowdsourcing to do this? All of where do you put these temporary locations? How do you share all of these things? So the approach is something along the lines like this. I'm not going to go into details of any of this at the minute, but just the big picture is we've got this digital twin style model where real-time information feeding into the system. On the top left, we've got this gamification stuff where we're trying to understand the rules about what's going on. In the bottom part, and this is what I really want to emphasize, in our agent-based model now, the computation in here is huge. It's not just a simple rule. Every agent may well be running a complex optimization algorithm to find the routing through the traffics or whatever. Going back to my data integration slide I had up earlier, there may well be a whole range of other machine learning models linking into that to help them guide what their decision-making is going to be. So it's no longer a simple, cooperate, defect, or whatever it's going to be. Or no, it is. But how I make the decision about whether I'm going to cooperate or defect is informed by lots of computation and complex processing. That's just to paint a picture of a really complex agent-based model. This is for L. Sorry. I'm not allowed to say that. It's all
I haven't seen a fish yet.
fish is coming. So this is where I started working with Yoshi a long time ago. So I've published quite widely in this evolutionary game space. If you can think about it in terms of, let's keep it simple, a prisoner's dilemma type game or a public goods game, where the agents playing this game have to make a decision about whether they're going to cooperate or defect. And perhaps if we map them onto graphs, their interaction parameters are going to change and whatever. And we can do a whole lot of experiments like that. Rather than just playing a prisoner's dilemma style game or a public goods game, I also have a paper about a trust game. That's a fairly recent one. And dating back a while ago, within your lab, real human experiments, which, I'm not really good at ethics. I don't know even how it works, but we build the models. This paper from Physical Reviewee, I think, is really cool with Alex and Yoshi there. And we're playing the game, a public goods game, but the decision-making isn't quite just, I'm going to cooperate or defect, but there's other attributes in the game which help us make the decision about what we're going to do. And that was based on sort of an Axelrod type model. So hybridizing these things to see what's going to happen. So there's some background papers. What I want to do is talk about this paper for about 10 minutes or so, and that might lead us close to the end. And this is where the fish comes in. So this paper was in Scientific Reports, and Burkhart was a PhD student. And Tim, who was a professor here in our school, his interest was more generally in multi-agent systems learning generally. My interest in this evolutionary game theory, how can we bring it all together to solve the problems? And I like this title because Helene, who's another PhD student I'm working with at the minute, is basically doing the same sort of thing as well. Slightly different versions of games on graphs and so on, but decision-making, trying to trade off what's the best strategy we should play. Common pool resources. I just like this picture because if we're going to use water, I just still don't understand why we grow cotton in the middle of Australia, but I don't know. Maybe you guys can tell me the answer. I just don't get it. Over harvesting water, what do I mean? So look at the date of this paper. This is when I first became interested in this work. On the top row, we have a group of players playing a game. In this game, we're going to harvest a certain amount of water. Everybody plays nicely together. We're able to maintain that water level, assuming that the water is replenished at an appropriate rate. In row B, players perhaps do not play together well. Perhaps one of them takes too much, or maybe all of them take too much. Maybe the resource isn't replenished at the right rate. We run out. So how can we investigate the decision-making of the players in this sort of game? A couple of people's there that perhaps you should be familiar with. We're talking about Tragedy of the Commons and Eleanor Ostrom's work in this space. Deforestation. Fish game. This paper from 2017 came out roughly the same time when we're working on this particular paper. If we over-harvest the fish, what's going to be left? So what is interesting to me in this particular game, yes, we can do this as a standard evolutionary game theoretic model to see what happens. But rather than doing that, how we treat this particular game is a standard multi-agent reinforcement learning problem. So multi-agent reinforcement learning problem. At the end of the year or the start of next year, I'm going to have about 20 students come up to me and want to do their master's project on reinforcement learning. They're just going to want to throw a deep learning model at something. And I go, why? And I'm going to talk about why in just a minute in this one. So multi-agent reinforcement learning. What I'm going to have here is a partially observable general sum Markov game. So it's defined by the parameters S, A, R, and P. The state, the action, the reward, and some sort of transition probability. I'm going to have a population of agents playing this game. The important part here is that the state transitions and the payoff depend upon the behavior of the other agents. To really make it a stochastic game, if you think back to the water example, we can just vary or make this replenishment rate a stochastic value as well. So if that's the case, how do I go about learning in this game? So the first part of the talk here on this particular game is about different reinforcement learning techniques. The reinforcement learning techniques are going to help us make a decision about harvesting. So what happens? The state space. The state space basically, N is just the volume of the resource. Volume of water, the number of fish, number of trees, whatever it's going to be. Then we're going to use a logistics equation to show the growth of that particular resource. Parameterize it. Change the RG value. It doesn't replenish as quickly. Change some parameters. Then we're going to introduce a harvesting function. Again, parameterized model. Change the values of alpha and beta. We can make it a simple problem, make it a hard problem without going into the details. We link all of these things together. So the resource is going to fluctuate over time. Time varying problem. How will reinforcement learning work in that sort of scenario? Obviously, if I change the RG and the beta and the alpha, it makes it either a really easy problem or a really difficult problem. From an agent-based modeling perspective, we sweep across parameters to show the effects of what's going on. We've got some hypothesis that we want to test. Our action space. The action space in this particular game is going to be the sum of all the individual actions. So the players make a decision, XI, what I'm going to do. The reward they get is going to be some function of the harvest, how successful the harvest was. But if everybody tries to take too much, they're not going to be successful. So how do you determine what is the most appropriate XI value? To make it a little bit more complicated, every time you do this, you're charged some sort of a value, C. So there's an extra parameter in here. So my reward depends on how successful I am at harvesting, the cost associated with it as well. And then there's going to be this state transition. To keep it simple, let's just say we just go to the next state without too many problems, but we can make it more complicated. Getting back to the title of the paper, what we do is balance our reward function between whether I want to concentrate on maintaining the resource at a sustainable level or maximizing my profit. So a trade-off between those two things. And this is where Helene's project is kicking in, where she's balancing this idea of, I guess, conflicting objectives to maximize our reward in a multi-agent reinforcement learning stochastic game. Standard reinforcement learning model, nothing tricky about this slide. The action, I've written it as A here, it's just to be consistent with the literature, but this is my X values here. But in our game, this is what we have. So the common pool resource game, we've got multiple agents. It's a little bit more complicated. So our goal in Burkhardt's initial paper, it was just using standard Q learning to see what happens. It didn't have to be Q learning. It could be any other reinforcement learning algorithm. That's fine. Go off, vary some parameters. Here, it's setting that weight parameter, balancing it between sustainability and making a profit to be even, change the number of agents. Yes, we get slightly different behaviors. We can see what happens. Take it to the next level. We vary that weight parameter just a little bit more and weird things happen, almost as you would expect. But we've demonstrated under particular conditions when sustainability might be the better option as opposed to profitability. In a stochastic, multi-agent reinforcement learning problem. I mentioned deep learning. There's always a student who wants to do deep learning. So hey, let's go and throw deep learning at it. My advice was, why are you wasting your time? We did it. And as you go through deep learning, there's a whole range of different parameters we can use to do this. And I'm not even going to go into the details, right? Just click on it. It's okay. It's the usual sort of thing about deep learning. Go and change the parameters. All we're doing is finding the parameters of a neural network. Okay. And what happens? Oh, some versions of it work better than the other. Okay. And some of them are hopeless. More importantly, the results simply just reproduced the results we had here, which was fine. And the important thing was, given our model, that trade-off is the key. But the trade-off in the parameter values is okay. But if I change the regrowth rate, so let's pretend we've got a pending drought or what's going to happen. Obviously, this is going to change. But we can use this sort of model to investigate those sort of scenarios quite easily. So I've gone from, get to this next part because I want to get to this one. So as we've gone through, we started off with the COVID model informed by the policy and real things. The key part from my perspective here was how I created that interaction matrix and drawn from real world. We went to the ABMs on the Roman Britain, completely thought experiment type thing where we couldn't validate the model. It's okay. Next one was a really heavy computational load for decision making within this freight sustainability network. The fourth one was this evolutionary game theoretic model, which might be more familiar to many of you. But in Elle's particular case, you're not using a reinforcement learning model, but you're doing other cool things in terms of the social networks. Sort of like that. To finish up, because I want to make sure you guys ask me lots of questions. This is work in progress. It's nowhere near complete at all. But why I want to mention this one, it's about how do we come up with the rules for an agent-based model? And Craig is the PhD student working on this. He actually has an interest in the dynamics of startup companies. What's going on? How successful is it going to be? Whatever. I have a bit more of an interest in the group dynamics more generally. Jen is his PhD supervisor from Melbourne Business School. And Gary's also involved there. Their name's going to come up in just a minute. So when we're working in this startup situation or small group dynamics, how do you influence other people? And we know there's the usual group dynamics and whatever. So that's our starting point. We're concentrating on this startup world to see what happens. So Jen had this paper which appeared, I think it was early last year. Social alignment theory of power. Social alignment theory of power. And I'll come back to this slide in just a minute, but I just want to define two terms. So when I'm talking about power in this particular context, I'm talking about the ability to induce change in another through the control of specific resources. Volitional influence, we're talking about stemming from features such as competency, status, and so on. So power, volitional influence. So what the paper was about was classifying these. And over on the right-hand side is what I'm most interested here. And I realize the text is pretty small, but you can dig out the paper. As I come down the slide, it's talking about prestige-based, dominance-based, persuasion-based, or passivity. I don't say that word, passivity-based. Different hierarchies. So what happened? Armed with this information, as a PhD student does, Craig went out and did a whole lot of trawling into literature to come up with related work about influencing in this particular space. And what he's done was basically characterized I can't remember the exact number, but there was a couple of hundred different types of behaviours out there. And from that work, I squashed it down a little bit to, I think, 97. From this 97 particular behaviours, which fall into this 2D matrix about corresponding to your ability to inspire or motivate versus your ability to force compliance. From there, a fairly detailed survey, which I'm not going to go into the details. Each one of these is one of those 97 characteristics. This is really preliminary work, but basically trying to work out what's going on. From there, and I'm only click this really quickly, come up with some summary data. But the key to it is, from this survey, how can I go away and inform what the agent-based model is going to be? So from that detailed survey, we're coming up with a range of characteristics of the individuals which we're going to put into our agent-based model. From that, the usual sort of agent-based model things, think about the social dynamics, where they're going to be. Then we're going to do the usual, explore the parameter suite, blah, 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 to see what happens. So I sort of come back in a circle talking about, if I'm going to build these agent-based models, how do I do it? How do I inform where the rules are coming from? It's that part. That's enough for me at the minute. I'm going to stop talking. Questions from somebody, anybody, please.
Hi, Mike. All right. Thank you. Thanks, Michael. So I really like agent-based models. And in my mind, I feel like, and kind of capture this, there's two different kinds, obviously a continuum. On the one, you have like your number 2 and 4, which were, you know, fairly simple and meant to sort of, what's the space of a theory, what's the, and then you have like 1 and 3 and maybe what 5 will turn into, which is, there are so many parameters and I'm going to just try to throw them all in and model. And so this is a question about 1 and 3, which always seemed to me very cool, but I don't understand how anyone can possibly do them. Like it seems wizard-like, right? I mean, there's so many parameters and so many dependencies. How do you know, or like you can't possibly just sweep the space of all of them. So how do you know, you know, what things to conclude or not, or what things to focus on? Yeah, I don't know. This is not that well defined of a problem, but it seems so hard to me.
I'll get rid of my mail.
Yeah.
I don't have an answer. I really don't. It's really, really difficult. I mean, if we're going to build an agent-based model, what's the purpose? Are we really trying to test a particular hypothesis, or are we using it as a bit of a thought experiment so that maybe you can go back and refine your theory and then go and do it? And how we do that is going to be very, very different. With the COVID one, as an example, of course, there's a big sweet load of parameters there that we have to deal with, but you cannot possibly do them all. So you have to do some black box stuff and lock things in. Different response, but with my project over working with the pharmaceutical companies, they're trying to step through, I'll make this up, a 7-step process. Now, there's no way we can build a simulation model for a 7-step process. So 5 of them are just completely locked in black box. Then from some of these other ones, we start to do that parameter sweep where we're just trying to address one small part that isn't necessarily the whole answer. It's just to guide what we're going to do. I don't think that was a good answer, but it's the best I've got.
It was an ill-formed question, so there you go.
Ill-formed response.
Thanks, Michael. That was super interesting. I think this question follows a little bit on from what Andy was asking, but I know in most the really cool reason why you use agent-based models most of the time, it seems like, is when you don't really have data or very good data, and so you're trying to explore what could happen under different assumptions. But I was curious about contexts where you could have a data set, like a validation data set, say an experimental data set, and how you might be able to use agent-based models as sort of a theoretical tool to understand what's going on. And so, for example, I've seen a lot of agent-based models looking at things like polarization, and a lot of what they'll do that for is say, like, look at all these different ways that polarization could happen, right? You could have rational agents or not rational agents, or you could have them interacting or not interacting, or different ways. But what if you had an experiment that sort of like got polarization in, you know, a lab setting, and you could compare other ways that you can like sort of fit, I don't know, in our language would say you could fit different models to the data and see, okay, what values or parameters do people seem to be, I don't know, seem to best describe what's going on, or what assumptions are actually happening. Can you use that in that sense when you actually had sort of a validating data set? I don't know, hopefully that makes sense.
Absolutely. And I hope that's what we're doing some of the time. So I didn't go into details of this one, but one of the projects when we're talking about the unemployment, both of them combined, we have comprehensive data sets talking about the trajectories of people going through all of these positions. Whatever. So what is happening is there are alternative theories being proposed about what's going on. Our agent-based model is going to be testing some of those things, and we want to see how closely it matches with what's going on. Does the agent-based model solve the problem? No. It's just a little bit more evidence to support what's going on. I like that. With the phishing game one, I've concentrated just on my multi-agent reinforcement learning model, right? But in that space, of course, we can explore a whole range of different decision-making strategies which are being used in those particular games to see how well it matches. So thank you.
Are there any practical implications for the pool, common pool resource?
Are there any practical applications?
Could there be any? I'm just wondering.
Absolutely. I could answer that, or I could invite somebody else to answer that question. I will answer, but let's use the classic one. If we concentrated just on water in Australia, talking about irrigation. So there's a finite supply of water, assuming it's not a flood zone, and farmers are able to take that water out. So if you take the water out of the Murray-Darling Basin upstream, it's not going to get downstream. So how do you balance what's going on? A real practical application. Did that answer your question? You want more? There's thousands of them, but that water one is a really important one. Up on level 8, as you go into where my office is, you'll see it's the CRC One Basin banner up there. Go and have a look at some of their projects as well.
Yeah, I think my question is very similar to Venkia's. So, but maybe yeah, so maybe you don't need to answer it. But I just wonder if like we have a very complex data set and we want to have build some agent modeling for it. Is there any good way to choose, like for example, I want to focus on the, let's say, this properties of the data set, and I want to let the agent-based model to, let's say, to simulate this perspective. Is there any way that we can choose from a very complex data set? Because in the real world, there are too many.
And I think I'll answer your question this way by looking at that particular picture. So I think you just said we've got this we have really large data sets. We've got some hypothesis or whatever that we want to check. Maybe what we should do first is, from our large data set, go and identify which variables or whatever we're possibly interested in. Then from them, just use that subset in our agent-based model. But it's that whole point of how we do that and integrate it, which is the challenge. Again, I don't have one clear answer for you. It is very problem domain specific. But that identifying what's going on, then also the other comment about parameter sweeps and whatever, it's not possible, of course, right? So for really large problems, how do we do that? An approach I've been working on more frequently is using Bayesian optimization approaches to pick those parameter settings that we need. And that falls into that whole design of experiment stuff. And that's a really common theme in my work in a lot of the projects at the minute. I think I answered the question well, but the look on your face means I didn't answer it.
Yeah, I mean, you answered, but I just...
You give me feedback. You're saying it's a hopeless answer.
Just on my class. Yeah. So I feel like there are two different approaches. One is just like you said, it's like a data-driven approach. We from the data we want to see like what's the important perspective. But I think there might be another, like maybe the model based or the, let's say, there is some internal mechanism from some other literatures. There are some evidence, just like you.
That's the whole point. That's right. So for the problem domain, what are our options? We can do it completely data-driven. I'll go back to my causal discovery example for a minute. If I use that large data set and go and do my causal discovery on it, it doesn't work. If I use some hypothesis or theories to say, I'm going to cluster some of these variables first, I'm going to do something, reduce the size of the complexity of the data set, then I've got a smaller data set, I run my causal discovery, it works fine. The data-driven approach works sometimes, depends on the complexity of the data. Hence my comment right at the start about what is complex data. It has a huge impact.
Yeah, maybe just one last question.
I'm happy to talk anytime up on level 8. Come and talk to me. I'm lonely. Van's going to ask one thing. Oh,
There's one last question.
Oh. I forgot about Zoom. Oh, did I? I forgot about Zoom. How do I get Zoom back? I've lost it. No, I've lost. Where's Zoom gone? Sorry, Zoom. Van, go.
Do you like to be surprised by your models? Why or why not?
I do like to be surprised, but I also prefer not to be surprised because I'd like to know anticipate what's going to happen. No, yes, I want to be surprised by them. I guess that question is a little bit about emergent.
Yeah.
Right. And emergent is absolutely fine, but I just get sick of people saying, oh, it's emergent dynamics because I didn't expect it. Like, I don't know, like, if I have a complex ODE, it does things I didn't even think about, but it's not, you know what's going to happen if you run it long enough. Surprise you. If we had more time, I'm not doing this now. The part of the talk I wanted to present was about strategic deception and surprise, and that's from an ARC project previously, so I like surprise.